Hey everyone, and welcome. Today, we're diving into a really cool chemical competition I like to call the sugar race. We're going to see how a clever little test can tell us which sugars are the quick sprinters and which ones are more like the long-distance runners. So let's get right to it. So here's the big question, right? Which sugar actually wins the race? You see, in the world of carbs, some sugars react super fast, while others take their sweet time. To us, they might just look like white powders, but chemically, they are worlds apart. We need a really accurate stopwatch to tell the difference, and lucky for us, we've got one. Every great race needs competitors, and in our race, we've got two main categories of sugars ready at the starting line: the monosaccharides and the disaccharides. Let's get to know our contestants. Okay, on one side, we have the monosaccharides. Just think of these as the sprinters. They're made of just one single sugar unit. That makes them simple, lean, and ready to go in an instant. Then, on the other side, we've got the disaccharides. These are our hurdlers. They're bigger, built from two sugar units stuck together. And before they can even get going, they have a hurdle to clear. They have to break apart first. And that little extra step, well, it changes everything. So, how do we actually time this race and see who's faster? Well, let me introduce you to our official stopwatch for the day, Barfoed's test. This is the amazing chemical tool that makes this whole thing possible. Now, Barfoed's test is specifically designed to tell two types of reducing sugars apart. And a reducing sugar is just one that's able to donate electrons to something else. The test can react with both of our competitors, but its real genius is that it can tell them apart based on one thing and one thing only: speed. And hey, this isn't some new technique. It's got some serious history. It was created way back in 1873 by a Danish chemist named Christian Thomsen Barfoed. So yeah, it's been a trusted tool in biochemistry for a very long time. All right, let's get into the science of speed. What are the rules of this race? What is it that gives one sugar such a huge head start over the other? Well, it all comes down to the chemistry of the racetrack itself. The racetrack here is what we call Barfoed's reagent. It's basically copper acetate mixed into a weak acetic acid solution. And that environment, that mildly acidic condition, is the secret sauce. It's everything. The track is intentionally designed to be a little bit tough, so it really favors only the fastest and strongest competitors. It's built for a sprint, not a marathon. And this is exactly where our sprinters, the monosaccharides, have their massive advantage. They are powerful reducing agents that are ready to go from the get-go. They react directly with the copper ions in that reagent, which gives them a huge lead the second the race starts. But then you've got our hurdlers, the disaccharides. Being bigger and more complex, they just can't react directly. They first have to be hydrolyzed, which is just a fancy science word for being broken apart by water. They have to split into two individual monosaccharides, and only then can they join the race. And yeah, that hydrolysis step, that is literally the hurdle they have to clear. It's this extra, time-consuming process that the sprinters just get to skip entirely. And in a race that's all about speed, that delay makes all the difference in the world. So what does crossing the finish line even look like in a chemical race? Well, when a sugar reacts, it reduces the blue copper ions in the solution, turning them into something called cuprous oxide. And this stuff forms a solid brick-red precipitate. When you see that red solid appear, that's it. That's the finish line. Okay, so now we know the competitors, we know the track, and we know the rules. How do we actually start the race? Let's walk through the steps for running the test and seeing who wins. It's actually incredibly simple. First, you add your sugar sample to a test tube. Then you mix in the Barfoed's reagent. Next, you heat the whole thing up in a boiling water bath. And finally, you just watch. You're looking for that brick red color to show up, but the timing of that heating step is absolutely crucial. And here is the single most important rule of the entire race. You heat the solution for a maximum of 2 minutes. Not 3, not 5, 2 minutes. That's the cutoff. So why be so strict about it? Well, if you heat it for too long, you're basically giving our hurdlers, the disaccharides, enough time and energy to break down and react. They'll eventually cross the finish line, sure, but that gives you a false positive. It makes it seem like you had a sprinter all along. That 2-minute window is what ensures only the true sprinters have enough time to win the race. All right, the timer is stopped. The race is over. Now for the best part, reading the results and finding out who's the winner. This table lays it out perfectly for us.
If you see that brick red color pop up within about 1 to 3 minutes, boom, you've got a winner. It's a monosaccharide, our sprinter. If it takes a lot longer, maybe somewhere between 7 and 12 minutes, then you know it was a disaccharide. And if after all that nothing happens at all, well, that just means you have a non-reducing sugar, like table sugar, which couldn't even compete in this race to begin with. Now, any good competition has to have rules about fouls, and Barfoed's test is no different. There are a couple of limitations. First, you can't use it on something like a urine sample, because the chloride ions in there will mess with the reaction. And second, if you have a really high concentration of a disaccharide, it might react fast enough to give you a false positive. You got to keep the conditions just right for a fair race. So, if you take just one thing away from all of this, let it be this. Barfoed's test isn't really about if a sugar reacts. It's all about how fast it reacts. It's a brilliant example of using the speed of a reaction to get an answer. Time, it turns out, is the secret ingredient that reveals the truth. And that kind of leaves us with a final thought, doesn't it? This whole idea of using time as the critical factor to tell similar things apart, it's just such a powerful tool in science. So what other scientific races can you think of where timing is everything when it comes to revealing hidden truths about the world all around us? Thanks for watching.